Okay. Okay, so in the last class, we were discussing various properties of information measures. So far, we've seen three different measures of information, the entropy, the mutual information, and the K divergence. And we've seen that the mutual information, K divergence, and the entropy can all be expressed in terms of each other. We also saw the chain rule for entropy, that is the entropy, the joint entropy of x and y is equal to h of x plus h of y given x, or h of y plus h of x given y. We also saw that the entropy is a non-negative quantity, and it's equal to 0 if and only if the random variable is actually deterministic. That is, it puts full probability to one particular value and it's 0 otherwise. And just as we had a chain rule for entropy, we also saw a similar chain rule for the mutual information. So the chain rule for the mutual information says that the mutual information between x and the random variables y, z is equal to the mutual information between x and z plus the mutual information between x and y given z. Okay, and similarly, what we can, I won't formally prove this in class, but I leave it to you as an exercise. But we also have a similar chain rule for KL divergence. So if we have random variables, or we have two distributions, pxy and qxy, then the KL divergence between pxy and qxy can be expressed as a sum of qx. So the divergence between px and qx plus the KL divergence between py given x and qy given x. And you can prove this pretty easily just by looking at the definition of the KL divergence between pxy and qxy, factorizing pxy as px times py given x and just splitting the terms within the log. Okay. Anyway, you can find this in the lecture notes that I've uploaded on Piazza. So any questions regarding the topics until now? Right. Any questions? Okay. So the way forward will be the following. I'm going to show that. So we've seen that the entropy is a non-negative quantity. In this and the next class, we'll see some more properties of the mutual information and KL divergence. In particular, we'll see that both the mutual information and the KL divergence are non-negative for irrespective of how you choose the parameters. And we'll also see some convexity and concavity properties of the entropy, KL divergence, and mutual information. So in order to prove these results, we'll need some properties of convex functions. Right? And that will really be the basis of the basic tool used in proving many of these results. And it's helpful. The tools that you will learn here, which is basically one theorem called so basically just one result called Jensen's inequality. This is very useful in many applications, not just in information theory, but also in statistics and machine learning. So it's a very widely used tool, and basically follows from basic properties of convex functions. So before I go to that, let us first recall what a convex function is. So suppose that I have a function f from R to R. So when do I say that this function is convex? So what definition of convexity have you seen before?
If there is 2 point A and B,
Okay.
and there are 2 points A and B,
Okay.
and then all the f of like a linear combination of f of A and B less than equal to f of A plus f of B. Sorry,
So
convex combination. Sorry, not linear combination. Convex.
and so for all alpha in 0, 1. So if I take any 2 points A and B, any 2 real points in R, and take any alpha between 0 and 1, then f of alpha A plus 1 minus alpha B is what is this equal to, or less than or equal to, or greater than or equal to?
Less than equal to.
Correct. So this is less than or equal to alpha times f of A plus 1 minus alpha times f of B. Right? So so f is convex if f of any convex combination of points is less than or equal to the convex combination of the value of the function evaluated at these points. And basically a geometric way of looking at this is that you know what a convex function looks like. It looks something like a bowl, right? And you take any 2 points A and B, any 2 points A and B, then alpha A plus, so this is the axis, this is A and this is B, then alpha times f of alpha A plus 1 minus alpha B will lie somewhere over here. Right, and this would be my f of alpha A plus 1 minus alpha B. On the other hand, alpha f of A plus 1 minus alpha f of B lies in the line segment joining f of A and f of B. So it's f of A, f of B, and this would be, and alpha f of A plus 1 minus alpha f of B would lie somewhere in between. Right? And so geometrically you can see that alpha for a convex function, alpha f of A plus 1 minus alpha f of B would always be greater than or equal to 1 minus f of alpha A plus 1 minus alpha B. Correct? Okay, so is there any other definition of convexity that you have seen?
Double derivative.
Yes.
What is it?
So what is the double derivative equal to for a
Greater
convex
than
function?
greater than 0.
Yeah, so it's convex if f is twice differentiable, then the function f is convex if d square f by dx square is greater than or equal to 0 uh, for all x in R. Right? In particular, you can define all of this for over intervals. So you say that f is convex over some interval, uh, say x1, x2, if this property holds for all a, b in the interval x1, x2, and similarly it's convex if the second derivative is greater than or equal to 0 for all x in the interval x1, x2. Right? And in fact, one can show that these two statements are equivalent to each other. I won't go through the details now, but you can take a look at the lecture notes that I've uploaded for the full proof. So one part of the proof is given in the textbook by Cover and Thomas, and the lecture notes has the other way around. So both these definitions are equivalent to each other. Okay. Any questions? So a very useful property of convex functions, something that you can see visually, is what happens to the tangent. So suppose that I have a convex function which looks like this. Let's say that this is defined in some interval, right? Okay. Now if I construct the tangent at any point, what can I say about this? If I draw the tangent, can you give me any property of the tangent in relation to the function f?
f dash of x.
Sorry, can you please repeat?
Derivative of x, sir.
Sorry, what is the derivative? So that is the slope of the tangent, right?
Values in the tangent less than the curve function values.
Correct. So irrespective of which point I choose, the tangent, so I have f of x, and let us say that I construct the tangent at some point, let me call this a. Okay, so this is the tangent constructed at the point which touches f of x at a at x equal to a. The tangent is basically a line, so it is some mx plus c. No matter where I construct the tangent, uh, the value of the tangent. So if you look at these two functions, f of x and mx plus c, f of x is always greater than or equal to mx plus c. So the tangent always lies below the curve, right? So no matter where I construct the tangent, as long as the function is convex, the tangent always lies below the function. Okay. Okay. And what is m equal to?
f dash of x.
Correct. So it's expected value of sorry, f dash of x. So, dx evaluated at x equal to a. Right? Okay. Now, so this is true no matter where I choose my x. Correct. Okay. So this property will be very useful. So for all a in the interval, the tangent y equal to mx plus c is always less than or equal to f of x. So using this, I will prove the following result. This is called Jensen's inequality. And it basically says that if I have a random variable x with distribution fx, and so it's a continuous random variable, or it could be a discrete random variable, it doesn't really matter, but it's defined over the reals or some subset of the reals. And if I have a function f which is convex, then the expected value of f of x is always greater than or equal to the f of expected value of x. Okay, so as long as f is convex, no matter how you choose your distribution px or probability density function fx, the expected value of f of x corresponding to this convex function f is always going to be greater than or equal to f of expected value of x. Right? And this turns out to be an easy consequence of this particular result that we had, where the tangent is always below the function for a convex function. Right? So in particular, I'm going to take, so f of x is greater than or equal to mx plus c for the tangent constructed at x equal to a. So what I'm going to do now is I'm going to take the point a to be expected value of x. So the expected value of x is some number, right? It is some number, and I'm going to choose the tangent constructed at expected value of x. So x is equal to the expected value of x. Right? So this is mx plus c. So now I have f of x is greater than or equal to m times x plus c, right? So if I take the expectation on both sides, then f of then the expected value of f of x is greater than or equal to m times the expected value of x plus c. Correct? I'm just taking expectation on both sides. So the expectation of f of x will be greater than or equal to expectation of mx plus c, and which is by linearity of expectation, it is m times expected value of x plus c. Correct? Any questions up till this point? Any questions?
Sir,
Yes.
do we consider a straight line also to be convex?
So yes, so straight line is indeed convex. In fact, it's both convex and concave.
Okay, sir.
So yeah, so maybe along that, yeah, okay. So I'll get back to that in a minute. Any other questions? Okay, so this, but note that. So what is the right hand side equal to? So the right hand side is the value of the tangent function at x equal to expected value of x. So this is ma plus c. Right? So at this particular point, since this point is expected value of x, but what is this equal to? So in terms of f, what is this equal to? What is the right hand side equal to?
F of E of X.
It's f of e of x, right? And that is because since this is the point at which the tangent touches the line, both the function values should be the same. Right? And so we get that expected value of f of x is greater than or equal to f of expected value of x. Okay, and this holds for any function, any convex function f, and any distribution on x. Okay, so now we've seen what happens for convex functions, and let's explore some related notions. Okay, so we say that a function is convex if either one of these properties is satisfied. So so f of alpha a plus 1 minus alpha b is less than or equal to alpha f of a plus 1 minus alpha f of b, or equivalently, the second derivative is always greater than or equal to 0. Now, if either of these, now if these inequalities are strict, that is, f of alpha a plus 1 minus alpha b is strictly less than alpha f of a plus 1 minus 1 minus alpha f of b, then we say that this is strictly convex. So it's strictly convex if this is a strict inequality. Okay, and we say that a function is concave or equivalently strictly concave if minus f is convex. right? So if you look at, if f of x looks like a bowl, then minus f of x would look like an inverted bowl. So if f is convex, then minus f is concave, and if f is concave, then minus f is convex, right? So now can you tell me what would be Jensen's inequality for a concave function? Then what can you say about and f of
F of x less than or equal to f of e of x.
correct? So expected value of f of x would be less than or equal to f of expected value of x, right? Any questions? Okay, so can you give me some examples of convex functions? So what can you say about x square? Is x square convex or concave or neither?
Convex.
It's convex, right? What about e to the power x?
Convex.
What about sin x?
Depending on the range.
Correct. So can you give me a range for sin x for which it is convex?
Pi to 2 pi.
Yeah. Okay. So between pi and 2 pi, it is convex. And what about another range for which this is concave? Okay, so someone says 0 to pi. Okay, and say what about log x?
Concave.
It's concave. Right. Okay. So now let's use the last point. So log x is concave. All right. Okay. So let's look at, so using the fact that log x is concave and using Jensen's inequality, we'll try to prove that the KL divergence is always non-negative. Okay. So to do that, let's look at the negative of the KL divergence. So dpq minus dpq is minus sum over all x, p of x log p of x by q of x, which is the same as sum over all x, p of x log q of x by p of x, right? But effectively, what is this equal to? So this is the expected value of, the expectation is taken with respect to the distribution p of log q of x by P of x. Correct? Do you agree? So I have the expectation of a log. What can I say about the log of the expectation?
It will
So
be
is this
than
great?
expectation of
It will be less than or
less
equal to 3x.
less than
So this is a less than or equal to, right? And now let's try to expand this expectation out, right? So this is log of summation over all x, p of x of q of x by p of x, right? So this is log, the p of x and p of x cancels. So what is the sum of overall x of q of x?
One.
It's 1, right? So this is equal to 0. So minus dpq is always less than or equal to 0, right? Or dpq is always greater than or equal to 0 for all pq. And one important thing to note is that since I'm only using properties of expectations over here, I can basically write the KL divergence as an expectation. It doesn't really matter whether the distribution is discrete or continuous. If the random variable is discrete or continuous, this result still holds. So dpq is greater than or equal to 0 for all probability mass functions p and q, and similarly for all densities fx and gx, the KL divergence is always greater than or equal to 0. Right? Any questions? So we basically started off with the fact that log x is concave. We wrote minus dpq as the expectation of a log of something, and we just invoked Jensen's inequality to take the expectation inside the log and that evaluated to 1. Okay. So now can you tell me when this is equal to 0? So when is dpq equal to 0?
P is equals to
P
Q.
equals to Q.
Yeah, so whenever p is exactly equal to q, this is equal to 0. If p is not equal to q, then this inequality is strict. Right? So if p is different from q, then the KL divergence is strictly greater than 0. Okay, so let's see some quick consequences of this inequality. Now, earlier, I've shown that the mutual information between two random variables I, x, y, this can be written as a K divergence. What K divergence is this?
PXY and PXPY.
Correct. So it's the K divergence between the joint distribution and the product of the marginals. Right? And now we know that the KL divergence is always greater than or equal to 0 for all distributions PQ. So this implies that the mutual information is also greater than or equal to 0 for all joint distributions PXY. And when is the mutual information equal to 0?
Independent.
Correct. So it's equal to, so now we've seen that the KL divergence is 0 if and only if the two arguments are equal to each other. And in this case, the mutual information is equal to 0.
PXY is equals to PX into PY.
Yes, so only if Px y equal to Px Py or x and y are independent. Right? Okay, that's good. But now we've also seen that the mutual information can be written as a sum of entropy or a difference between entropy and conditional entropy, right? So what is Ixy equal to?
HX minus XY.
Correct. So hx minus h of x given y. And we know that the mutual information is always greater than or equal to 0, which implies that h of x is always greater than or equal to h of x given y. Right? So the conditional entropy is always less than or equal to the entropy of x. And this, therefore, conditioning cannot increase entropy. Right? Now, another useful or nice property is that now let us take any distribution Px. Okay, and now we know that dqx Px is always greater than or equal to 0, right? Or maybe let's use dpx qx itself. So dpx qx is greater than or equal to 0 for all distributions qx, right? So this is sum over all x p of x log p of x by q of x. This is greater than or equal to 0, right? Now what happens if I take qx to be the uniform distribution? What is q of x equal to?
One by x.
Constant.
Yeah, so 1 by cardinality of x. Cardinality of x. Right? And now I'll split the terms within the log. So it is sum over all x, p of x log p of x plus sum over all x, p of x log cardinality of x. So this is greater than or equal to 0. Right? I'm going to take the second term on the right hand side. Okay. So what is this equal to? The second term, this over here. Yes. So what is this term equal to?
Log cardinality of x.
Correct. So this is just log cardinality of x, which is greater than or equal to, and what is this equal to? Minus
Entropy of
summation. Yes.
H of
Minus
x.
entropy of h of x.
Correct. So this quantity is a negative of the entropy of x. So if when I take it to the right hand side, I get a plus. So this is h of x. So irrespective of what distribution you choose, for any discrete distribution, the entropy is always less than or equal to the log of the cardinality of x. Right? And when is it achieved? So when is h of x equal to log cardinality of x?
When it's uniform distribution. Uniform distribution.
So it's uniform distribution, right? So the maximum value of the entropy of any random variable is equal to log cardinality of x, and is achieved only if x is uniform. Right? And the reason why it's achieved only if x is uniform is because this inequality is strict. This inequality becomes an equality only if px is equal to qx, right? Or when px is equal to the uniform distribution. Right? Any questions?
Hello, sir.
Yes.
So why did you replace qx by 1 divided by cardinality of x?
So again, it's a trick, right? So this is valid for any pair of distributions p and q, and I basically chose qx to be 1 by cardinality of x, just so that I would get this particular inequality, h of x less than or equal to log cardinality of x.
Okay, sir.
Any other questions?
So can we extend this definition to continuous systems also?
So which definition?
The inequality we are telling entropy is less than cardinality.
So that's hard, right? So what do you mean by equal to the cardinality?
Logarithm of cardinality. Like, what does cardinality mean in terms of continuous function? I wanted to just have an analogy.
So that doesn't really work for continuous random variables, right? But what is certainly true is that Okay, so just as you said, let us suppose that a function. So let us look at all possible distribution probability density functions which are supported in a finite interval. Okay, so fx of x is greater than or equal to 0 for x lying in some interval, let's say a comma b, and it's equal to 0 for x outside the interval a comma b. Okay, so if you look at the probability density function, you have a b, so it's allowed to be non-negative only in this particular region a to b, but is 0 everywhere else. Right, so if we have this particular restriction on the PDF, and now I can choose I can use a similar approach, right, for using the fact that the KL divergence is always greater than or equal to 0. So if I choose Qx to be the uniform distribution on A to B, then what is Qx equal to?
One by b minus a.
Correct. So it's 1 by b minus a. Right. So then I would get the KL divergence fx Qx is always greater than or equal to 0, or integral a to b f of x log f of x by 1 by b minus a. This is greater than or equal to 0, or basically rearranging, I get that the differential entropy of x is always less than or equal to the log of b minus a. Right. So if you have a constraint that the random variable is non-zero only in a finite interval, then the differential entropy is always less than or equal to the log of the size of the interval, or basically this turns out to be the differential entropy of a uniform random variable. Well, this is of course under the restriction that uh, that f is non-zero only in a bounded interval.
Okay, sir.
Okay. Any other questions? Okay, so maybe this is a good time for a quiz. I put it up in the chat box, and if you're unable to access this, just let me know. Okay, so maybe you can take 1 more minute. Okay, so is there anyone who has not submitted yet? Anyone who hasn't submitted? Okay. All right. So yeah, so I see that Anu has asked a question in the chat box. What can you say about the entropy between x and the entropy of xy? Okay, so you have h of x comma y. Now if I use the chain rule, what do I get? I get h of x plus h of y given x. What can you say about h of y given x?
So it will be h of y if they are independent.
Correct, but in general, what can I say about h of y given x?
Uncertainty measure of y by knowing x.
Correct, but what can I, so can I say that this is always greater than or equal to 0?
Yes, sir.
Yes, right. So h of y given x, just as we saw that the entropy is always non-negative, the conditional entropy is also non-negative, right? So h of x plus h of y given x is obviously going to be greater than or equal to h of x. So the joint entropy between x and y is greater than or equal to h of x. And when is it equal to h of x?
Y equals to x.
Sure. So y equal to x is one particular case, but in general, whenever y is a function of x, whenever
Yes.
it's a deterministic function of x, h of y given x is equal to 0. Right? So the joint
So in
entropy
the same
between, yes, please. Go
so
ahead.
in the same manner, then h of xy is greater than or equals to h of y by x,
It is true,
since
of
h
course.
of x is
Yes,
greater than or equal to 0.
yes. But you can say something more, right? So h of x, y is greater than or equal to h of y, right? Which is greater than or equal to h of y given x, because conditioning can only reduce entropy. Right? Any other questions? So we'll end the class for today. But yeah, if you have any questions, you can ask them now.
Sir,
Yes,
in the assignment, you have assigned a text file for us for the last
correct,
question, sir.
correct.
Generally, we do have ASCII values for spaces also. Do we need to consider space
Yes,
between
you should.
letters?
You should.
Okay.
So consider all ASCII characters, including space, punctuation marks like commas, full stop, quote, everything else. In case there are any non-ASCII characters, you can ignore them.
Okay, sir. Thank you, sir.
Okay, so if there are no further questions, I'll stop the recording.